phosphorus halides PCl3, PCl5 can also be used. All these methods are substitution reactions, SN2. So you will see that there is an inversion of configuration. Inversion of configuration, if there is a chiral carbon, then only you are going to see, for example, this OH is being converted to Br, but this is not a chiral carbon because this is CH2. Chiral carbon is here, and if the chiral carbon is there and the reaction is not taking place on the chiral carbon, inversion will not happen. Inversion is going to happen only if you have a chiral carbon. For example, this one, this OH is present on a carbon which is connected to 4 different groups. Now if you put PBr3, this is SN2 reaction. Reacted with PBr3, this is SN2 reaction, means inversion will take place. So Br is going to come from the side opposite to that of OH. Got it? So this thing you should keep in mind. But here the SN2 has occurred, but no inversion has happened. So this could be surprising that if I tell somebody that SN2 has occurred but no inversion has happened. Okay, because there was a chiral carbon and the reaction has not happened on that chiral carbon. Got it? That's why. Next is, so I hope everybody is able to see the screen, and if there is any problem, just stop me anytime. Okay, and in this case we are treating glycerin or propane 1,2,3 triol with PCl5 3 moles, and we get propane 1,2,3 chloro compound. Okay, that is 1,2,3 trichloropropane. Okay, this is OH being converted. So the shortcut, you know, if you take PCl5 and if you react it with alcohol, the shortcut is going to be like this, right? PCl3, put Cl and Cl. So you are going to end up with RCl, HCl and POCl. So these are the substitution reaction, SN2 reaction. That's only you need to remember. If there is a chiral carbon on which the Br or Cl is OH is attached, then carry out the inversion. Next is nucleophilic substitution at aryl halide. This is a very important thing. Okay, and the nucleophilic substitution on single bonded carbon, that is sp3 carbon, that is actually SN1 or SN2. If it is a smaller alkyl group, that is SN2. If it has larger alkyl group, then it is SN1. Got it? So, but nucleophilic substitution on benzene are not SN2 and SN1. They are bimolecular NAS. Is it clear? Bimolecular nucleophilic aromatic substitution. As you can see over here, you have a chlorobenzene, and this doesn't happen with aqueous NaOH. Okay, that happens at the reaction with aqueous NaOH. Happens only on the sp3 carbon, that was SN2. This is not SN2. This is bimolecular nucleophilic aromatic substitution. Okay, this is going to be a very difficult step because, and in order to compensate the low reactivity is because of the resonance between the chlorine and the benzene. In order to overcome the low reactivity, you took very high pressure and high temperature. Okay, look here. So here also you are taking a very high temperature. But as you have more and more NO2 groups, the reactivity is increasing and the temperature which you have taken is coming down. The reaction is happening with very easily. And if you have 3 NO2 groups at ortho and para position, the reaction can happen very quickly just by water and warming little bit. It is because NO2 is an electron withdrawing group, so it is going to bring in the positive charge. So this NO2 will bring in the positive charge at the 3 positions. Similarly, this NO2 will also bring in its positive charge because of the resonance at the 3 positions. Okay, so if the group, wherever the group is present, the positive charge will come at its ortho positions and para positions. Now, we are mainly concerned about this position. Now we have taken NaOH, and this position which is connected to Cl has lot of plus charge on it because of the NO2. So it has become very reactive, and it has become reactive. So the Cl can react very easily and it will be displaced by OH. But this is not SN1 or SN2. This is addition elimination mechanism or bimolecular NAS. Look how this is happening. So first of all, SN2 can't happen here because the Cl can't come out directly by an OH being connected simultaneously. That can't happen because you have a pi electron cloud which of the benzene ring, which is stopping the OH minus to come and displace Cl minus directly. So what happens over here is, as you can see, the OH minus first comes in, it pushes the pi bond and it get attached. Okay, this is going to be a very difficult step, slow step, because the ring is aromatic and you are displacing the negative charge. Now this minus charge is temporarily stabilized by resonance within the ring, and here you can see the minus charge is being passing through the position carrying the NO2 group. So this minus charge is very much stabilized by resonance. Okay, and this minus will not continue to stay in this way because this is an intermediate. This is going to come again. It is going to form a double bond again, but someone has to move out of this position because carbon cannot make 5 bonds. So if this is trying to form a double bond, the group which is more weaker, which has a weaker bond, which can come out easily, which is electronegative, will come out, and this group is none other than the Cl minus. So Cl minus will come out, and finally you have OH in place of Cl. This reaction is addition elimination mechanism or bimolecular nucleophilic aromatic substitution, not SN2. Okay, that happens. SN2 happens on sp3 carbon where you have all single bonds. Got it? This is for SN2. So I hope this is clear to everybody. But presence of electron withdrawing group at ortho and para position increase the rate of reaction because ortho and para positions, if groups are there, they are going to bring in the positive charge and make the benzene ring more reactive towards the attack of nucleophile. The attack of nucleophile is going to happen more easily if you have NO2, but where the NO2 should be there. The NO2 should be present at ortho and para positions with respect to the leaving group. Got it? So let's compare this. Arrange the following compound in increasing order of the rate of reaction. So A is the reference, it is neither faster nor slower. And if you have NO2 at ortho and para position, look, the positive charge is going to come in and will make the position more reactive. But if it has meta position, the positive charge by resonance is not going to come on the Cl, carbon atom carrying the Cl. So this will not become that reactive. Is it clear? So its reactivity is going to be less. So this is the most reactive B. Then you have C is reactive, little bit more reactive than A. So you are going to have C, B, A as answer. But if you have electron donating group, the rate is going to decrease. Okay, it is going to decrease. So which one of the following represent Dow's process for the manufacture of phenol? So this also method is used for the preparation of phenol, as you can see, and this is known as Dow's process, very famous method. Okay, but not with aqueous NaOH. It requires very high temperature. So Dow's process is preparation of phenol from chlorobenzene by reacting it with NaOH at high temperature and pressure. So these are some other methods, and we are going to study in the next chapter today. So let's discuss this. Here the solution becomes acidic. This is polar protic solvent. This is tertiary carbon. And this is it an aromatic halide or aliphatic halide? It is an aliphatic halide because the Br is not connected to benzene. It is connected to the normal group. So Br can come out easily. This is not like the one which we discussed above today. And the solvent, you can see, it can help the Br to come out and stabilize the cation because it is a polar protic solvent. So Br will come out. You have a cation, and ultimately who is going to come and join in on the cationic position? The solvent itself. So this is SN1 mechanism. You have OET being connected to it. This is SN1. But what happened to Br? The Br left the reactant and you have HBr, H from ETO, OET, ETOH. So the solution becomes acidic. But the air with aqueous ethanol, the solution is not going to become acidic. This Br can't come out until unless you take a very high temperature and pressure. You can see over here what temperature we are dealing with. Got it? And very high pressure. So Br is not going to come out. Here with aqueous NaOH, no high temperature pressure is given. F minus can be liberated, but there is no high temperature. But why it is being liberated? It is because the NO2 group is present at the para position, and this makes this very reactive. It brings in the delta positive charge on the carbon atom carrying the chlorine. Okay, so F minus is going to come out, but this F minus is not coming out. What's the reason? The reason is because it doesn't have NO2 at the para position. You need to have an electron withdrawing group at ortho and para, and that electron withdrawing group by resonance it is going to bring in the positive charge on the carbon atom bearing halogen. But in this case, as you can see over here, if NO2 is not directly connected and NO2 will not do the resonance, there will be no plus charge. Okay. So here F minus is not liberated. So this is a very, very important basic question to tell you the difference between the substitution happening on aliphatic halides and aromatic halides. Aromatic halides, either they require very strong conditions if there are not strong conditions, the aromatic halide should be very reactive. It should have NO2 connected directly to the benzene ring at ortho and para positions, not this one. Okay. The last one is the elimination reaction. So elimination reaction, elimination, as you know, is means removal of two groups and no other group take the place of those two groups. So if you remove two groups, what happened to the bonds? What happened to these two bonds? So these two bonds get connected among themselves in order to satisfy their valency. And if these two groups which are removed are from adjacent position, this elimination is known as 1-2 elimination. Okay. 1-2 elimination or alpha beta elimination lead to the formation of an alkene. Elimination of alkyl halides requires strong base, alcoholic KOH, and elimination requires heat, high temperature. Why it requires high temperature? Because you are forming a pi bond, and you know the pi bond is weaker. So why a strong bond is being broken and why a weaker bond will form? You need to provide energy. Got it? You need to provide energy, so you need to heat it. If you heat it, then only elimination is going to occur. So elimination occurs with the presence of strong base, alcoholic KOH, NaNH2, NaOET, sodium tertiary butoxide, means O minus on tertiary butyl, in the presence of heat. But substitution is easy because you are replacing one sigma bond with another sigma bond. In substitution, you use a mild base or a weaker base, that is aqueous KOH. Got it? So aqueous KOH, if you are going to use, the substitution is going to happen, and alcoholic KOH, if you are going to use, elimination is going to happen. So I hope this is clear, right? So let's see here also. So how this elimination has happened. So just like substitution, SN2 bimolecular and SN1 unimolecular, there also we have E2 and E1. If you take a strong base will on its own start the reaction by extracting OH minus, and the electron of the H plus will get with the carbon-carbon bond, and this double bond start forming, and but carbon cannot make 5 bonds, so Br simultaneously start coming out. So this is just a single step, just like SN2. SN2, the OH minus was directly hitting the carbon bearing the Br. In elimination, the OH minus is actually, OH minus is not hitting the carbon because the carbon is tertiary. So OH minus can't come in here. But OH minus can easily take away the hydrogens. There are 9 hydrogens around this carbon. They are more easily accessible. Okay. OH minus will abstract the H plus. The electron density will come in and you have a double bond. Okay. Because it is a bimolecular, just like SN2, this is E2. The rate is dependent. This is a single step, no rearrangement, single step reaction. Rate is directly proportional to the concentration of base and hydroxide. Single step reaction, transition state involves abstraction of H from the beta carbon by the base and removal of leaving group and formation of pi bond. So I hope this is clear to you. Okay. So let's move on to even. Suppose if you, so there also in SN1 even most of the students get confused. So whenever you use a strong base like OH minus, OET minus, okay, whenever you use them, they are going to start the reaction, right? And two molecules get involved. So there you have bimolecular transition state, and that is SN2 or E2. If you are taking heat, strong base, E2. If you are taking aqueous base, that is SN2. But if you have taken a base or a nucleophile which is neutral, then you are going to have SN1 or E1. For example, if you have a weak base like water, water is a base, but a very weak base, being neutral, it is weak. So it is not going to go and abstract the H directly. It will not attack. So the reaction doesn't involve two species. It involves only one species, the substrate itself. What happens to the substrate? The substrate automatically self ionizes because this is a polar protic solvent. It facilitates the departure of Br and carbon. You have a carbocation, got it? And the carbocation formation is slow step. So once you, so this is the slowest step which involves just one molecule. That's why E1, elimination unimolecular. It is not a single step. First step involves slow ionization of the leaving group. Then if you apply heat, the solvent molecule takes away the H from the position adjacent to carbocation. So these electrons are going to get shifted between the cation and this carbon, leading to the formation of a double bond. So this is elimination unimolecular, just like SN1. This can also lead to SN1. This can also lead to E1. But which one will happen at what? What are the appropriate conditions? So the whenever you have a heat, do the elimination reaction. That's the important thing. Two or more steps. Rate determining step involve the departure of leaving group and formation of carbocation. Abstraction or removal of H by base and the formation of pi bond occur in the fastest step. Okay, that's is fast. That doesn't control the rate. So rate of E1 is directly proportional to the stability of the carbocation. More stable a carbocation is, more easily it is going to form. Okay. Better the leaving group, faster will be the E1 and E2 both in both the cases. In E2 you require strong base and heat. In E1 you require weak base, which is none other than the solvent molecule. Got it? So this is how the reaction is happening. And now the question is, which alkene, if there are more than one type of hydrogen available around the carbon atom carrying the Br, Cl or I, which alkene we are going to form as a main alkene? So the answer is more branched alkene, which is formed towards the more longer alkyl group, larger alkyl group is the major alkene. So here you have two hydrogens. Hydrogen you have removed from this. So you have a double bond. This is more branched alkene and this is less. This is known as ZZ alkene or Z7 alkene. The spellings could be different, but the meaning is same. So more branch alkene is a major product. So here also, if you form alkene on the with a smaller alkyl group like this one, it is going to have just two alkyl groups around. One alkyl group. This is disubstitute. If you form a double bond towards a bigger alkyl group, you have a three alkyl groups around the doubly bonded carbon atoms. So this is more branched alkene, more stable alkene, and this is known as ZF or Z7 alkene. And this is going to be the major product. So always remember, in elimination, we are going to get major product ZF alkene as a major product. So which one of the following alkyl halide gives only one alkene as a product of E2? Only one type of alkene. I am not talking about the main and major alkene and the minor alkene. I am asking only one. If you consider all alkenes, only one alkene is formed. So if you take this is a symmetrical molecule. So if you remove HBr, either from that side, upper H plus or lower H plus, you are going to get a cyclopentene. Only one alkene you are going to get. But if you have this, you are going to get two different alkene, one on this side, another on this side. Here also you are going to get two different alkene. These two are same, so I am considering only one alkene. Here also you are going to get two alkenes, different alkenes from this side and this side. So one alkene is you are going to end up with only with B. Got it? Now, which alkene is formed as a major alkene? Here also we should consider the same principle of ZF alkene, which is formed when you remove H from more branch side, and you can see over here the bigger alkyl groups are this benzene and CH2. This is benzylic group and ethyl group. These two are the groups. But from where? This is the Br. So I am going to remove the hydrogen, which lead to an alkene which is more stable, which has more number of alkyl groups. But this side and this side, the alkyl groups are going to be same, but the alkenes are going to be of different stability. You are going to remove the hydrogen from the left hand side because the alkene formed will be more stable because of the benzene. It will be able to undergo resonance. This one, conjugated alkene. Conjugated means the one which is stabilized by resonance, and that alkene is going to be the main. And this is the ZF alkene. Okay. The other alkene which is less branched like this one, that is Hoffman alkene. That is minor product formed in less amount. So next question. So here you have, this is an elimination reaction as you can see. And double bond being formed towards benzene side. This is the major product, but this is less substituted alkene. More substituted alkene would have been on this side, but that is not forming. What could be the reason? The reason is the presence of benzene that is more important than number of alkyl. If so, double bond, if there is a benzene, double bond you should make on the side on which the benzene is present, because this double bond is going to participate in resonance and will make the alkene stable. Okay, the product is formed due to nucleophilic substitution? No. This is an elimination reaction. The product has formed according to the Markovnikov rule? No. This product has formed because of the Sedzev rule. Conjugated double bond product is formed due to higher stability because of the resonance stabilization by the benzene ring? Yes. Is a better leaving group? No. This is not a leaving group. This is a base you have taken. Leaving group is OTS. Sulfonate. Toluene sulfonate is the leaving group. This is a good leaving group. This is O and TS means this. Toluene sulfonate. Paratoluene sulfonate. This whole group is known as. So it can come out easily because O minus is stabilized by resonance. Just like Br, this is a leaving group. Shall not produce propene by reaction with HBr. Okay, HBr you have added and okay. Followed by elimination or direct only elimination. So which is not going to form. Propene is not formed under any condition by C. Those who do not have 3 carbon atoms. Now the last part, that this SN2, as we have seen, the SN2 and E2 can happen simultaneously and they're competing with each other. In substitution reaction, the nucleophile comes in an attack on the carbon atom. And when you have the carbon atom, okay, you get the nucleophile attached and remove the leaving group. Similarly, if you have a tertiary carbon atom which is branched enough, the nucleophile can't come in because of the crowding. So nucleophile, now it is not known as nucleophile, it is known as base because it can't come and join itself to the carbon. It will takes away the H plus and you will have a double bond. That is elimination reaction, right? So both can compete. This one can come in and remove the Br. This is substitution happening, and there is no problem in substitution happening on this ethyl bromide because you have a small alkyl group. And substitution can happen very easily here. Okay, so you have a ether being formed. But if you have exchanged the alkyl groups with O minus and Br, suppose if I take O minus with the ethyl ethoxide and Br with the tertiary butyl, you may think that the same thing will form, but this is not going to happen because in this case O minus will come and attack on this carbon, which is not possible because this carbon is a very bulky carbon, it is highly branched. So it will not let the nucleophile to come and attack on the carbon and remove the Br. But that doesn't mean the reaction doesn't happen. Reaction happens. So SN2 becomes very difficult if you have a tertiary carbon atom. Clear? So now what is going to happen? It is going to come and take away the H plus, which is easily accepted. So now you will have an elimination happening. H plus being removed from the adjacent carbon, Br being removed from this middle carbon. Direct attack of the nucleophile was not possible So this is E2. If you want to prepare ethers, you need SN2 to happen because you need O to get connected to the alkyl. You don't want the alkene to come. So remember, wherever you are having a halogen, there that carbon should be primary. That carbon should not be tertiary. Because if you have a tertiary carbon, in tertiary carbon the substitution will not happen, elimination will happen. So this is Williamson ether synthesis, which we will discuss more in this chapter of alcohol, phenol and ethers. That is for the preparation of ethers. So preparation of alcohol, if we talk from alkenes, it is very easy. From alkenes, preparation of ether, alcohols. As you can see, you can add water. So addition of water is known as hydration. But pure water, is very less reactive. It doesn't have enough H plus ions. In pure water, the H plus ion pH is 7 and the H plus ions are just 10 to the power minus 7. So you take H2SO4, dilute H2SO4 you take. Dilute H2SO4 is a catalyst, and that's why this is known as acid catalyzed hydration of alkenes. Okay, and that lead to the formation of an alcohol. How the H plus and OH minus are of the water of the H plus and OH during the acid catalyzed hydration are going to come and join in, and this is governed by the stability of carbocation. This is governed by Markovnikov rule. In day before yesterday's class, in the first class also we have seen Markovnikov rule. Okay. So H plus is going to come and join in to the carbon atom where you already have H plus. So here you have H. So H plus will come and join in on this carbon. Why this is so? Because you are getting a tertiary cation which is more stable, and on this you are going to put the water OH. Similarly, H plus will come and join in to the carbon atom which already has H plus, more H. So rich gets richer. Wherever you have more hydrogen, the hydrogen is going to come and join in at this position. You will have a cation here, and the OH will be connected at this position. Okay, so this is Markovnikov rule. Markovnikov rule actually, you are going to put the H plus ion where you have already having more hydrogens. Okay, and you can, in layman language, you can remember it in by saying rich gets richer means H plus is going to come and join into the carbon atom bearing more hydrogens. But actual thing which is working behind it is the stability of the carbocation. So out of the two options, you should try making both the carbocation by joining H plus on both the sides. So you have a more stable carbocation which is being formed. This is tertiary. This is tertiary. Okay. More stable carbocation which is being formed. Okay. So that is the underlying reason for Markovnikov reaction to happen. Okay. So H plus, I should generalize the statement. Instead of saying that H plus should attach itself to the carbon atom bearing more hydrogens, I should generalize the statement by saying that H plus is going to join itself to the doubly bonded carbon atom such that a more stable carbocation is formed. A reaction such that a reaction proceeds to more stable carbocation. Okay, that is the underlying reason. Okay. So here the more stable carbocation, you can think this is tertiary and this is secondary. So you are going to form a cation over here. This is secondary carbocation, this is tertiary carbocation, you are going to have a cation here. So accordingly, you are going to add. Acid catalyzed hydration of alkene except ethene lead to the formation of. Yeah, except ethene means if you have any higher alkene, okay, addition of water leads to the formation of alcohol. But what type of alcohol? Primary alcohol, secondary alcohol. Okay, let's say if you have propane. So this is primary carbon, this is secondary carbon. The cation is going to come on the same, more branch carbon. And here you are going to put the OH from the water. So you are going to end up with the secondary. Okay, as per the Markovnikov rule. If you have this alkene, this is primary carbon, this is tertiary carbon, and you are going to have OH here. Okay, this is tertiary alcohol. So all alkenes except ethene will have more alkyl groups, more carbon. So they are going to get connect their OH group on the internal position where the carbocation is more stable. So either you will end up with secondary or with tertiary alcohols, but not with primary. I hope you are getting my point. Okay, primary alcohol is actually outside. Cation is not stable there. Okay, clear? So let's see this. This is the mechanism you can see. So you have H plus and you have two options. Either you can shift the double bond like this, or if you can put the H plus and shift the double bond like this. So if you follow this option, okay, you have a carbocation. So I will remove this because if you shift the double bond in this way, you have the double bond is removed from this carbon and you have a plus charge over here. Look, and now you will put the double bond. Now you will put the not the double bond, OH group. So H got connected to the carbon atom bearing more hydrogen. Got it? So I hope this is clear. So you ended up with tertiary alcohol. But be careful that because you are proceeding to a carbocation intermediate, carbocation always have a tendency to shift. But there is a criteria for shifting. The criteria is that it should become more and more stable. Suppose if it is a primary carbocation, it should become secondary after shifting. If it is a secondary carbocation, it should become tertiary. It should become more stable. If it is becoming more and more stable by shifting onto adjacent position, it will shift. So it's our duty to check whether the shifting is possible or not and do the shifting of the carbocation. Okay, and then put once it is the shifting has completed and you have a more stable carbocation, then put the OH. So rearrangements are possible, I should say, in this. So let's see here. So this is primary, this is secondary. The H plus is going to form on the secondary cation. H plus is going to come on the primary because you have more hydrogen, and the carbocation is going to form on the secondary carbon, which is a more stable carbon. Once you have this, the carbocation can shift here. It can become more stable. Further more stable, it will become tertiary, that I know. But which group at this position? This position already has H, methyl, and methyl. So which group is going to get shifted towards the carbocation, and the carbocation should come at this tertiary position. So which group should I choose to take it on the other side? So the shifting will be as per the migratory aptitude. Hydrogen, then phenyl group, then tertiary group, then secondary, then primary, and then CSC methyl. So H is going to shift because H can shift more easily. It has more migratory aptitude. This is the migration tendency. You have methyl, its tendency to shift is less. Hydrogen tendency is more. This you should remember. So I shifted hydrogen, that led to a cation, and this cation ultimately has become more stable tertiary cation, and now put the OH in the place of the cation. So this is the final answer. Got it? Clear? Next is, suppose, so acid catalyzed hydration of alkene with dilute H2SO4 always may lead to shifting of carbocation. That we should remember. If the carbocation is more stable, form can stabilize itself, it will shift. Got it? That is very important. But suppose our conversion demands an alcohol where no shifting has taken place. If I ask you some compound preparation of compound where the no shifting is required, the H and OH are being added to the double bond only, not by shifting onto some other place. So there I should use oxymercuration and demercuration. That is also addition of water, but not by taking dilute H2SO4, but by taking mercuric acetate, water, and NaBH4. So there you get the water being added in a Markovnikov way. But the difference is the carbocation which is formed will not shift on to some other position to become more and more stable. You have directly, wherever you have the double bond, just H and OH on that. No shifting. When no shifting? When you have taken oxymercuration and demercuration. Got it? Oxymercuration and demercuration is carried out in the presence of mercuric acetate and water. THF is the solvent, followed by NaBH4 and H2O. So this is how it has happened. Here the shifting will not occur. So suppose if you have taken the above molecule and if you add water by using oxymercuration, demercuration, mercuric acetate, H2O, THF, NaBH4, then do the addition in Markovnikov way. Attach the H wherever you have more hydrogens. So I have put the H over here along with the two hydrogens. Put the OH on the adjacent carbon, but no shifting. Got it? I need not to show this H atoms to compare these products. Here the shifting has occurred and here the shifting has not occurred. Got it? That is the difference. Okay. So if you want to prevent the shifting, use mercuric acetate. Why the shifting doesn't occur? That's the reason is very simple, because you have a cyclic mercurinium ion as the interface. And because of this cyclic mercurinium ion, the shifting doesn't occur. The cation gets the electron from the mercury, so it doesn't want to shift here and there. So this mercury stops the shifting of carbocation, right? And then you add OH and all. And with NaBH4 you remove mercury also. So ultimately you have just water being added, OH being attached to the more branch side but without shifting. So in this case, oxymercuration demercuration of the given product of the given compound produces the major product. Which is the major product? Markovnikov addition. Still we are going to follow the Markovnikov rule, but without shifting. So this is going to be the answer. But suppose if you would have taken dilute H2SO4, then the OH will shift at this position, because the cation will get shifted towards the benzene. Benzene being more capable of stabilizing the cation, so cation will get shifted and OH you will ultimately have on this carbon. But with oxymercuration demercuration, with mercuric acetate, no shifting. Wherever your double bond is, put HNO there only. Now till now we have seen Markovnikov addition only. What about anti-Markovnikov addition? So in Markovnikov addition, either by dilute H2SO4, which was happening in a Markovnikov way, but with shifting, which may happen if the carbocation gets stabilized further. Next is next is Markovnikov addition without shifting. That was by oxymercuration demercuration. That has happened. But suppose if I want to put the OH group, and both of these methods, okay, they were leading to the attachment of OH group inside. But suppose if I want the OH groups to be added in anti-Markovnikov way, means outside, and H inside on the internal carbon atom, then I'm going to use hydroboration oxidation. So I'm not going to put water directly. I'm first going to put HN boron, and then boron is oxidized by H2O2 and NaOH. So that ultimately attaches H and boron, and which boron is being replaced by OH, so H and OH is being attached. But boron being a larger atom, okay, boron, because it is a larger atom, so boron has a tendency to attach outside. Means if suppose if you have more branch on one side on outer carbon, boron will attach itself to the outer carbon, and that carbon you have OH being attached finally after doing the oxidation with NaOH and H2O2. Okay, so this you can see over here. So this is anti-Markovnikov addition of water, which is you have used B2H6 or BH3 and THF and NaOH and H2O2. Propene to 1-propanol. 1-propanol means you want to put the OH out on the outer carbon. If you want to put the OH on the outer carbon, go by hydroboration and oxidation. This is the way. Okay. So what's the mechanism? As I told you, boron being a larger atom will try to attach itself on the doubly bonded carbon which is lying outside. So H and B will be connected in this way. Ultimately this BH2, so H and B, this is also a syn addition, that also you should remember. Syn means hydrogen and boron being added on the same side. Then you have H, boron being getting added to other two, because boron has 3 hydrogens, so it can add to 1 alkene, it can get to 2 more alkenes you can say. So ultimately you have this H and boron being connected to alkenes, 3 alkenes, and you have trialkyl borate. Then you use alkaline medium, and in the presence of hydrogen peroxide, which removes this boron and put the OH in place of boron. So you have an alcohol, but that alcohol is being connected on the outer carbon. So this is a very, very important question which is being asked in JEE mains. Okay, so what is going to be the answer? I have compared the two methods. This question is asking about the two methods. So A is oxymercuration and demercuration. The addition is going to be the Markovnikov addition. Got it? And H being connected outside and the OH being connected inside, but there will be no rearrangement. While the B, you have an alkene, and this is anti-Markovnikov addition. Anti-Markovnikov addition means OH boron outside, because boron is a larger atom, so it will not attach itself inside because it will feel more repulsion. So boron will be connected outside on the outer double bond, and on the outer double bond you have OH being connected. So this is anti-Markovnikov addition. So A is Markovnikov product and B is anti-Markovnikov product. So this was the question in JEE mains. So I hope you understood this. Okay, very simple. Okay, very simple. Just you need to know. But if I would have taken dilute H2SO4, then also I would have obtained Markovnikov addition product as per the Markovnikov rule, but with shifting. Okay, so then the OH may be present somewhere more inside where you had three alkyl groups, methyl groups of one. On that carbon you will have OH because the shifting or the stabilization may have lead to shift. Okay, so I hope this is clear to you, right? Now a very famous method, not only very famous method for the preparation of alcohol but for the preparation of other functional groups. Okay, this is a very important method. So let me tell you a very important thing, and this is why Grignard reagent RNDX. A very important thing is a very important thumb rule. Wherever you want to attach a carbon atom, extra carbon, think of Grignard. If you do not want extra carbon, don't use Grignard. If you want extra carbon, extra alkyl group, more carbon atoms you want to put on the compound, think of Grignard reagent. So what is it? So Grignard reagent, alkyl halide is there, alkyl halide you react it with magnesium, and this becomes an organometallic compound. Organometallic compound means you have a carbon and metal bond. In carbon metal bond, actually you have negative charge on carbon and positive charge on metal, because metals are electropositive. So this is how it is prepared. Very simple. You mix the alkyl halide and magnesium in the presence of ether. You heat them. You get a Grignard. In the Grignard, you need to remember that the carbon which is connected to magnesium is bearing a negative charge. So all your problems will be sorted out if you remember this, not this one, this one. Okay, for example, if I ask you to react bromobenzene with magnesium, you are going to get this one. This is the Grignard. So there is a minus charge on the benzene, plus charge on the magnesium. Magnesium is a metal. If there are two halogens, the weaker one, whose bond is weaker, will react quickly. So this is MgBr. And F is stronger bond, so it is not going to react. Got it? So this is how, this is the preparation of Grignard. Now how we are going to do its reaction and how we are getting alcohols. Okay, so that is very simple. So first of all, you need to take a compound which already has oxygen and double bond oxygen. Now the Grignard is added to it. The alkyl group of the Grignard has negative charge, so it get connected to double bond. Okay, so now what happened to the double bond oxygen? Because the alkyl group from the Grignard is coming in, the double bond will change to single bond. Upon acidification, you will get it as OH, means alcohol. So you start with some aldehyde or a ketone. You can see over there. You react it with Grignard. So this is an aldehyde or a ketone. I have just shown you the options by putting it in bracket. This Grignard is going to come in. It is going to add to double bond O, O minus, MgBr plus. Look, this is being added. Okay, because this is why the addition has occurred. This is minus, and this carbon had plus charge. Okay, so that is why you are having a carbon alkyl group being added to it. Now, if you put water, this O minus will turn itself to OH. So you have an alcohol. But the alcohol doesn't have the original, not only it has the original alkyl groups, the two which were present or the one which were present, it also has the alkyl group which is added through Grignard. Okay, so suppose if you start with aldehyde, which is having one alkyl group, if you put in Grignard, you will have two alkyl groups. Okay, so you will have a secondary alcohol. If you start with the ketone is having two alkyl groups. If you react it with Grignard, you will have three alkyl groups. You will end up with a tertiary alcohol. So let's see here. So this is an aldehyde. It doesn't have any alkyl group. Look, only hydrogen, smallest aldehyde. If you react it with Grignard, you have one alkyl group connected to this carbon of the aldehyde, because this is plus. So you have one alkyl group connected to this CH2. You have a primary alcohol with one extra carbonate. Suppose if you take an aldehyde which has one alkyl group and one hydrogen, one alkyl group is already there. Another one comes and join in with the help of Grignard. Okay, so you have two alkyl groups now, and the double bond O will change to single bond O and it will become OH. So you have secondary alcohol. If you start with the ketone is already having two alkyl groups. You react it with Grignard, this alkyl group comes and join in. Now you have three alkyl groups, 1, 2 and 3. Two were originally present, two were originally there. The third one you brought in with the help of Grignard. So you have a tertiary alcohol containing three alkyl groups. Got it? So very, very important. I hope you understood this. Okay, but if you do not have any alkyl group, then you have just CO2. Two 2 double bond oxygen, that is CO2, and if you bring in the alkyl group through Grignard, you have just one alkyl group. But out of the 2 double bond, only one addition has taken place. You have just one single bond and one double bond being left. So you have a carboxylic acid. So this is how the Grignard works. The reaction is very simple. Okay. So let's do this. What is going to be the answer to this question? It is a mixture of reactions which we have seen in previous classes and in this class today. So first we have reacted with the phosphorus and I2. Phosphorus and I2, you know, it is a EI3, right? Got it? Clear? EI3 reacts with OH and gives you I. Then you reacted with magnesium. Then you reacted with an aldehyde which has 2 hydrogens. Okay, we have just now seen it. And finally, you reacted with water. After Grignard, you need to water to neutralize that O minus. So which alcohol are we going to end up with? So are we going to get butanol, butyl alcohol, propyl alcohol, propanol? Okay, so this is quite easy. Will become I, this will become MgI. Okay, ET, ethyl magnesium iodide. And this is going to react with formaldehyde. Okay, now you have it will change to single bond after addition. Addition is reverse of elimination. So and this is going to change to OH. So you will have a primary alkyl group with one extra carbon atom. So you are going to end up with N-propyl alcohol or propane 1-ol. That is its IUPAC name. Now do always, by taking Grignard, do always addition happens? Or there is something else which can also happen? Definitely, not every time you have additions happening. Some other type of reactions can also happen. The other type of reaction could be acid base. Okay. Other type of reactions could be your elimination reactions, substitution reactions. Okay. We need to look at the reagent or the substrate which is provided to us. So let's see this question. This question is basically not the regular one. You will have Grignard, and it's what it means. This is CH3 minus and Mg plus. Okay, that means metal has plus charge, carbon has negative charge. Will the addition reaction happen? Answer is no. No addition reaction will happen. Why? Because you do not have a polar double bond. The polar double bond with plus and minus, the addition is going to happen on the plus. This is carbon-carbon double bond. Both have same electronegativity, so it is not polar. Now, then what is going to happen next? If the addition is not going to happen, what else can happen here? Carbon doesn't have a positive charge. It was there in aldehydes, ketones, carbon dioxide, because there the carbon was connected to doubly bonded oxygen. But here it is not connected. So what should we do? But there is something else where you have a positive charge, and that is H plus. Remember, this carbon is sp hybridized. This is electronegative. Okay, and because electronegative, this H is having delta positive charge. Okay, and electronegative charge is there. So this carbon is going to come and break this H plus. Got it? Clear? This carbon. So this is not addition. This is acid base reaction. So what are we going to get? What are we going to do? This CH3 minus will extract the H plus, and you are going to get the methane. Clear? So I hope this is clear to you. Okay. Acid base reaction. Acid base reaction happens when you have acidic hydrogen. Acidic hydrogen is there in carboxylic acid and HCl. But in alkynes also you can have acidic hydrogen, because the terminal hydrogen is connected to sp hybridized carbon, which is electronegative. So hydrogen connected to electronegative atom is acidic. So alkynes, terminal alkynes can have acidic hydrogen. Okay. So if acidic hydrogen is there, you are going to end up with methane. Okay. Next question. So which combination, which set of Grignard and ketone can lead to the formation of 3-methyl hexane 3-ol? So such questions are most common questions of Grignard. So first of all, write what it is. 3-methyl hexane 3-ol. Look, there are 6 carbon atoms. Third carbon you have OH, and on third carbon you have a methyl. Okay, this is the structure. For sake of simplicity, I have not written the hydrogen. They have written only the skeleton. Okay. Now you can see here, there are 3 alkyl groups, 1 alkyl group, and 3 alkyl groups are methyl, ethyl, and propyl. One of them is going to come in through Grignard, and the other 2 should be present on the ketone. Okay. Suppose if you take hexane 3-ol, hexane 3-ol is like this. Can this happen if we react it with CH3? The ethyl is already there, the propyl is already there. You need one more methyl, and that methyl can come and join in by Grignard. So yes, ethyl and 2-pentanone. Can this lead to the, let's see. Though we have the answer A as the answer, but let's see. Pentanone, 2-pentanone. 5 carbon atom, 2 pentanone, and you have methyl and propyl. Okay, followed by hydrolysis. You put ethyl. Can this form? Again, yes. So this is not one. I think I've made a mistake. This is more than one correct option. Yes, this can also happen. Suppose if you take 2 butanol, okay, this you understood. Methyl is there, ethyl is going to come in, and propyl is there. We need 3 alkyl groups. Let's see whether the C option is going to give us the same alcohol or not. So we just started with 2 butanol. This is 2 butanol. And you bring in the propyl group through Grignard. Yeah, okay, then also it will happen. Propyl we are bringing into Grignard, methyl is already there, and ethyl is there. Okay. So C4H9 MgI, this is butyl. And propanone. This is going to be wrong option. Because see, we have 2 alkyl groups which are 2 methyl. We do not have 2 methyl. We have just 1 methyl. And this is bringing in, attaching the butyl group. We do not have any butyl group. This is propyl, ethyl, and methyl. So this is going to be the incorrect option. And first 3 option will lead to the formation of 3-methyl hexane 3. Got it? So that's how you are going to select. Very simple technique for you need to follow for preparation of alcohol by Grignard. I told you very simple trick. First look at the group present on the ketone or aldehyde. Then one group attach one more group through Grignard. That's it. Very simple. Now Grignard can not only react with aldehyde and ketone, it can also react with esters and other carboxylic acid derivatives like acid chloride. So here what is the trick? First let me tell you the trick. During the first addition, first of all, such functional groups, carboxylic acid and derivatives, can react with 2 moles or 3 moles of Grignard. Because they have a group which can come out, which is a leaving group. So one Grignard is consumed by addition during the addition that one leaving group comes out. So one Grignard alkyl group of the Grignard comes and joins it. Then the next Grignard is going to come and join in on the double bond. You are having a single bond OH. Got it? So let's see over here. So first Grignard is going to come and join in, and it will remove this group. This is a good leaving group. It will come out. You have a methyl being connected in place of OR dash. Next you have methyl again coming in, but now you do not have any alkyl group, any leaving group, so it is going to come in. Both are alkyl group, they are not going to come out. Now you have 2 methyl and the original R group being connected to it, and you have a tertiary R. So on aldehyde and ketone can undergo addition of Grignard only one time. carboxylic acid derivative like ester and acid chloride can add 2 moles of Grignard. So if they add 2 moles of Grignard, two similar alkyl groups will appear on the final product. And the one alkyl group from the original compound will continue to persist. Got it? This is how you are going to form the product. So this is also same question, and I hope it is very easy. So how you are going to prepare this alcohol? You can see this is phenyl, this is methyl and ethyl. You need to bring in 3 alkyl groups. 2 should be present and 1 you should bring in with the help of Grignard. So ethyl you bring in and methyl and phenyl should be there. Yes. Methyl and ethyl are there. Phenyl we can bring in, yes. Phenyl and ethyl are there. Methyl we can bring in through Grignard, yes. And here the phenyl is there and there is a leaving group. You have taken Grignard. This Grignard is going to come and join in. Cl will be removed. And again the Grignard is going to come in. The Cl will be removed. So you have 2 ethyl groups similar connected. So this is not going to work. Because do not have 2 ethyl groups, you have just 1 ethyl and 1 methyl and 1 phenyl. Got it? Yeah, which of the following will react? Yeah, this is quite simple. Primary alcohol. This is going to give you secondary alcohol. RMDX if you take, it is going to give you secondary alcohol. Primary alcohol with 2 more alkyl groups, you are going to end up with this. The ring is going to break because of the angle is same, and this is giving us tertiary alcohol. This is giving us primary alcohol. This is going to give us secondary alcohol. This is some different compound. This breaks actually because of the ring, and it gives a primary alcohol with 2 more carbon. So same question, 2 phenyl ethanol. When you have phenyl magnesium bromide, pH. So this is going to come in, this ring is going to break and you are having pH CH2, and this ring is getting open and O minus, so you are having pH CH2, okay, so this is the answer. Next is preparation of alcohol by reduction. The straightforward method is by reduction. Take any aldehyde or ketone, react it with hydrogen and the presence of catalyst is going to weaken the bond of hydrogen. It will reduce the activation energy. The catalysts are D block elements having vacant D orbitals. They are PT, PD, Ni, ruthenium. Okay, PT, PD, Ni is the most reactive. Okay, and you are going to get the double bond O being reduced to OH. Okay. Ketones will give secondary alcohol, aldehydes will give primary alcohol. Very simple, catalytic hydrogenation reaction. But there are other types of reductions which are not using the catalyst, which are using H minus, hydride donors. Okay, like sodium borohydride, lithium aluminum hydride, and they